are the electrons being shared by the two atoms there? Where do those, well, we know, based on Niels Bohr's model, you have an atom. The atoms are like the solar system there. You have a positively charged center, and the electrons are circulating around that positively charged center. Now, when you put two atoms together, what happens to all the electrons there? Well, we say the core electron stays uninvolved in forming the chemical bond there. Okay, we'll go with that. But what happens to the valence electron? How are they being shared? Are those two valence electrons now circulating around two positively charged center, or they pretty much stays in a particular region where right in between the two positively charged center? What happens to the shared electrons? That, I guess, is what we're trying to get to. So for hydrogen atom, we know each hydrogen has one valence electron. Okay, they share with one another and they form a hydrogen-hydrogen bond. In this case, what happens to the atomic orbitals? We say that atomic orbitals start to overlap a little bit. In terms of measuring the energy about each of the hydrogen atoms there. Now, if you have individual hydrogen atoms, and when they are far apart from one another, there is no interaction. Okay? And so each atom of hydrogen exists in a singular form, requires quite a bit of energy there. Now, this red line in this graph there represents the amount of energy required when you have that particular situation. You can see two individual hydrogen electrons there. In theory, they can actually exist. Okay? However, they are not stable. If you put those two hydrogen atoms closer to one another, they start to get attracted, because here you have a positive center, positively charged, and proton, you have a positive proton here, electron clouds. So positive is being attracted to the negative, and the positive is being attracted to the negative. So they tend to get attracted to one another, they tend to get close to one another, and at a certain point, when you reach the optimum distance for the hydrogen atom there, somewhere around 74 picometer, the coexistence of the two hydrogen atoms in the molecular form requires the least amount of energy. Now, in theory, you can push those two hydrogens closer to one another, and then the closer they get, the more repulsion they will experience, because now you have two positively charged centers too close to one another, two electron clouds from each of one from each hydrogen atom, and they're getting too close to one another. They start to repel. So the most stable form of a hydrogen molecule is when they have a distance of 74 picometer between the two positively charged centers. Anything too close will result in repulsion. Anything too far apart from there will also result in a requirement of higher energy, eventually a separation of the two electrons. Now, if you look at this diagram, actually, it's very philosophical. It tells you something about human relationship. When you don't know each other, there's no attraction, and then you know each other, and you fall in love madly, and you get married, and then you step on each other's toes, and you start to push one away, and you. That may be the height. When you describe human relationships, sometimes you say, there is no chemistry between these two people. Where do you think that term comes from? That's why you need to learn chemistry. It's not only about the atoms and molecules, and it's also about human relationship there. Knowing enough chemistry will help you to determine when you step on each other's toes, is, hey, this is the time that I need to take a step back. Maybe we need to find that optimum distance between the two of you, so you will stay happily ever after. Okay, so that's one thing about the chemistry bound. Well, maybe there is something about chemistry in every aspect in life. So the valence bond theory goes that the two electrons, well, the two atoms, when they form the chemical bond there, they will overlap. Well, so what happens to the atomic orbital? The atomic orbitals from each atom will overlap with one another. Overlap meaning they are going to occupy the same region in space. Okay, so in this case, a portion of both orbitals occupy the same region in space, and that's what we mean by overlapping. So in this case, there are two different ways for the atomic orbitals to overlap. One is what we call the sigma bound, a single bound. The other is pi bound. We used those two terms already right before the break there when we're talking about the geometry of the molecules there. We say the pi bounds in multiple bounds do not count as a single electron pair or a single chemical bound there. And we're only counting the sigma bound there. Sigma bound refers to the single bound. Pi bound refers to anything in a multiple bounds in addition to the existing sigma bound there. Anything in addition. Double bound will be one sigma, one pi. Triple bound would be one sigma, two pi's. Okay, so there are two different ways for the atoms to overlap with one another. So in a situation where hydrogen and hydrogen combining with one another form a hydrogen molecule there, you have a sigma-sigma overlap to form a single bond. And when you have hydrogen fluorine, which is a polar molecule here, okay, and the sigma electron, well, the 1s electron is overlapping with the 2p electron. So 1s orbital is overlapping with the 2p orbital. You form a hydrogen fluorine sigma bond, a single bond there. And when you have fluorine, the 2p orbitals will overlap with one another, forming a single bond there. Okay, so this is one type of the overlapping where the sigma bond is formed. It can be between a sigma and a p orbital, and can be between p and p orbital. Could be, s and s orbital, s and p orbital, and p to p orbital. And if the d orbitals are involved, then also d orbitals can also overlap to form single bond there. Okay, so what happens here is that when the two atoms are getting close to one another, the valence electron will stay right in between those two atoms. That's where you have the highest electron density. Now remember the quantum theory, we're talking about the probability. Those two electrons 100% confined in this region? Well, we can't say 100%. Well, probably 90-95% of the chance these two electrons will stay in this region being shared by these two atoms there. So we say the electrons occupy the space right in between along the bond axis, right in between those two atoms there. And that's the region where you have the highest electron concentration, or electron density, if you will. So that's a sigma bond. Now, the other type of overlapping is what we call the pi bound formation. And the pi bound formation is that the two p orbitals, or in that case, the unhybridized p orbital. We will introduce the hybridization, orbital hybridization in just a little bit. So the two p orbitals overlap from side by to form a side-by-side, side-to-side overlapping there. Okay, so in this case, we say that the overlapping region is slightly above and below the bound axis. So in this case, the pi bounds are weaker than sigma bound, and pi bounds do not exist by itself. Whenever you have a pi bound, there has to be a sigma bound connecting the two atoms first. And then if you have more electrons there, electrons will occupy the unhybridized p orbital. We'll talk about the hybridization in just a little bit there. So pi bounds do not occur by themselves. When you see a double bound, there's one sigma, one pi. When you see a triple bound, one sigma, two pi's. Okay, so this is what happens in terms of the overlapping. The pi electrons can actually occupy either the